Hey Ryan, are you here?
Yep, I'm here.
Good morning.
Morning. Final stretch. Made it.
Yeah, just a remark. There's a typo on your schedule for today. Today's we start at 8:40
Ah,
with
oops,
final
yeah.
remarks.
Yeah. So I copied and pasted from the previous day, and I guess it bit me in the butt. So yeah, let me fix that real quick. That's what you get for copy and paste and trying to take the easy route.
Yeah.
All right. Yeah, I'm fixing it right now.
So the only reason why I guess like if students come up like at 8:30, they say, oh, 8:50.
Yeah.
They might think that.
All right.
And I will have another question for you about the photo.
Uh-huh.
How do you deal with, I think it's a great idea and I hope they will cooperate, but how do you deal with, like those that turn on the cameras and those who do not? And then, like for me in my screen, it was when there's more than 25 participants, I have like, I need to, there's a little arrow that said like, look, go through the second page of screenshots. But how do you make sure that you can have all the ones with the camera on, like on one screenshot, and leave the other ones behind? Is there a way to do that?
Yeah, I'm not. I know you can do gallery view to have like everybody like at the top.
Yeah. So on the gallery view, so yesterday when we were 46 or 43, so I had I couldn't fit everybody on one screen, and I had the arrow to scroll through another page of gallery. Maybe you don't have that, which is great.
Yeah, I'm not sure. I mean, this is going to be the most people I've ever had with the camera on, so this is going to be kind of like a test session as well.
Thanks for correcting this.
Yeah, so yeah, I got that fixed up there. I'll do some research today to see how many and if there's any ways around it. But what I was going to do is I was just going to make a full screen on my second monitor because it's a lot bigger than my laptop screen, so that may capture everybody. And then if not, I can do a screenshot and then go to the second page and get a screenshot and just kind of Photoshop them together.
All right. I mean, whatever you think is best. And I was thinking to do the Zoom photo after the Q&A panel, because typically there are more participants showing up for that session than anything else.
Yeah, everybody's gonna drop out early on the last day. It's Friday.
Well, for the office hours, we only had about between 20 to 28 students showing up. So,
really?
So a lot do not come to the office hours.
Well, maybe hopefully that's a good sign that they don't need any help.
I hope you're right.
Okay, so I just looked it up. It says you can fit 49 participants in gallery view.
Okay.
So
well,
I think
that should do it.
Yeah, except I tried to click on the article to go to the Zoom website, and the page isn't there. So. Yeah, so I mean, it says, depending on your computer, you can display up to 49 participants in gallery view.
Mm-hmm.
And then, because I'm gonna make a full screen to take the picture.
Okay.
And then if I need to scroll, I'll scroll and put them together. But I think we should be fine.
Okay, great.
And then I was thinking more about the waiver stuff. I don't think they signed any waiver for the previous years because I've always done the group picture, and I don't think they signed a waiver for it because it's optional.
Okay. Yeah, and I guess the one who do not want their picture taken, they're just not turn on the cameras.
Yeah, because I mean, there's ways in Zoom that you can, in gallery mode, you can have it to where if they don't have their camera on, they don't show up. So their name won't even be up there either.
Yeah. Yeah. And so yeah, I don't think for me it's going to be an issue because they're all most of them gave us a picture of them for their bio, and
Yeah.
it's on the website.
Mm-hmm.
But you know, I just don't want to get in trouble.
Yeah, I mean, I'll ask around before I post it up, but pretty sure it'll be good because I don't remember any waiver or whatnot. But I'll just double check.
Okay, that's fine. Like, I think you're right. Yeah.
I think the students really like the Slack.
Yeah,
It's been pretty active.
which it's great. I didn't know what to think. I'm so glad you suggested it because at the end they did self-organize.
Yeah. So I mean, they organize those breakouts for themselves during breaks. So
Yeah, but what I found in this oh, hi Mauricio, we're not alone anymore.
Oh, sorry.
No, you're good. No, you're good. Don't go anywhere. You're good.
I should to leave and enter.
No,
later?
no, don't worry.
Okay,
Don't
sorry.
worry. Don't apologize at all. How you doing?
I'm fine, and you?
Good. What? Which university are you from? I forgot.
University of São Paulo in Brazil.
Oh, cool. How's it going over there?
Sorry?
How are you guys doing in Brazil, like with all the COVID stuff and?
It's so hard here.
Yeah.
Yeah,
Oh,
because the coronavirus.
yeah. Sorry to hear that. I don't know if you have it worse than we do here. I just heard once that it was getting out of control in Brazil, but it's getting out of control here too.
Yeah.
For some places, but
Yes. Depends of the state. For example, São Paulo is it's big, a big city, and the cases is increasing quickly.
Mm-hmm. Yeah, how many people live in Sao Paulo? It's like over 10 millions, right?
Yes.
Yeah, that's
I think it's like New York. I don't know. I have never been there.
yeah, it's crazy because Colorado, let's see. How many people live in Colorado? Not that many. Oh, okay, more than what I thought. In the entire state of Colorado, we have 5.8 million.
Yeah.
This has increased. So yeah, you can fit twice, like 2 or 3 times the population of Colorado in Sao Paulo.
Yeah.
God, it's so many people.
So many people.
Hmm. Hi,
Hi, I made
Elizabeth.
it.
How's it going?
Well, first my badge wouldn't work. Then I come in and hook up my computer and no internet. I'm like, "Wah." So I just did a restart, Ryan, but I did get to see Mark. So
Oh,
thank
he
you.
still came over there?
Yeah, thank you for summoning him. I appreciate
Okay.
it. I just thought like, oh, are they doing work today? Not thinking people are in the building. Like I just, my mind was like, wow, but okay, all good.
So I made you the host, Elizabeth. Do you want to make me
Thank you.
co-host?
Yes,
quick? Okay.
yes, I will for sure.
And then I made Gunter co-host before you got in here too, so you should be good.
Okay. Yep, Gunter's
Alright.
co-host too. Yep.
Gunter, whenever you're ready to go, you can just share your screen and it'll kick me out. Unless you
I'm
want-
trying and it's not kicking you out.
That's not kicking me out. I had more power.
Well, now it is. Or
Oh no, I just stopped. Yeah, I stopped
Oh.
sharing.
oh, okay.
All right.
Good. People are joining by the.
Guess let's wait one more minute. Seems like people are coming in.
Today's the kind of day up here everybody wishes that they were here. It is so, so beautiful.
Oh, just wait. It's supposed to get like 95, 94 today.
Oh, really? Oh, wow.
Well, I mean, that's what it is for Lafayette, but Boulder's usually cooler.
That difference is probably not statistically significant.
Thanks, Alice.
It is really nice and cool right now. I was thinking like, oh, it almost feels like fall. And then I looked at the forecast and I was like, oh, damn it.
Yesterday it was like 55 when I woke up. I was actually cold with the windows open.
All right. In the interest of time, I'm going to start, and when people keep plugging in, well, we can catch up to us. Good morning, everybody. And so today's our last day. Every good thing comes to an end. And I'm going to start by saying, just similarly to yesterday, please, if you're not opposed to it, turn on your cameras. I know it's a morning pictures and morning face are not necessarily the best, but it's still nice to see people besides my own moving picture. But only if you feel like it. So today's announcement and closing remarks, I'm going to give you a bunch of information about what comes after the meeting, only if you want. But there's a tradition that every single tutorial, especially in-person tutorial, that we do a group picture just to record it and put it on the website. And what we would like to do this morning after the Q&A session is to take a screenshot of the Zoom panel with the Zoom gallery with everybody on. So at that time, hopefully you wouldn't mind turning on your cameras so we could just do that. It's optional, of course. If you don't want your picture to be taken, keep your camera off. Today, for the office hours, you're going to have the choice of different topical practical activities. And there's going to be experts for these activities present during the office hours. And we have 6 topics: land ice, atmosphere, ocean sea ice, land, VGC, and water and chemistry. And the way we're going to try to do this is going to assign 1 breakout room per topic, and the expert will be placed in these breakout rooms. And if you really need a one-on-one help with a helper, then you could get out of your breakout room and go into another, and Elizabeth will handle the logistics with this. At any time, you can get out of your topical breakout room and join another. And at any time you want, you just get out of your breakout room and then tell Elizabeth, hey, can I go to the one of that topic? And she would send you there. I know we sent you the link to ask question on Slido. And since we're going to do those different breakout rooms, what I'm going to do before the session starts is send a relevant question to the different helpers in each breakout room. And then you're going to use the chat on the Zoom chat to ask your questions with the helpers. Given the statistics based on the survey you answered yesterday, right now you're not going to be more than 10 per breakout room. And in most of the breakout room is much fewer than that. So it should be manageable. Now, after the tutorial, what is going to happen? We are preparing a survey for you to fill in, so we can get feedback from you, and so you can tell us more about how this week went, how you felt about it, what could be improved, what needs to stay, etc. We'll send you a Google Doc for this, so please look at your emails and respond to the survey as much as you can, and be constructive in your comments. Even if it could be, it doesn't mean that the comment has to be just positive. It could be, you could argue about that something didn't go well, but if you can suggest a way to make it better, it would be great. Also remember, when you fill in your survey, is that everybody here on the tutorial volunteered their time. We don't have a special account key to charge for this. And also keep in mind, it was our first time organizing a full Zoom tutorial. So the project code that you've been using to run your simulations, there is 155,000 core hours left. So that's plenty, and it will still remain up and for you to use until the end of August. If it's still not used up by that time, and I see that you guys are still running on it, I will ask for an extension so you can make the most of it after the tutorial, and it will be up until the account is spent. We had a question yesterday about what happened if you try to apply for another CSM tutorial, especially if it comes back to be in person. I have to say, unfortunately, you participating in this one makes you not on the top of the list and participating in the future one. And typically, if you've participated in one, we say, sorry, like there's not much else you're going to learn by participating in a new one, so you won't be accepted as a participant. And to give you an idea, we had 160 application this year for 40 spots. So there's a high ratio, and we need to give priority to participants who do not know about CSM yet. But what we encourage you to do after this tutorial, and now that you know more about CSM and how it works, is to become part of the CSM community. The community of CSM, we typically, we have different working groups, and I will show you a page after that that has chairs and co-chairs. They're the one who define and lead the scientific direction of the working groups. You have the scientific liaison, which are the first point of contact of whenever you have a question about the component that you're trying to work with, whether it's a scientific question or a question about the model component. We also have software liaison. Like if you run into a problem when you try to run with CESM on a given component, you can always try to reach out to them. And all this information, you have this link here, and those slides will be posted on the CSM website. If you click on it, and let me make this bigger, and hopefully you can see this. You can see all the different working groups. There's atmosphere, land, ocean, biogeochemistry, and you have the science liaison and the software liaison names here. And when you click on the name, it would send you to the email address. You have met all of the liaison of the working groups during this tutorial, during this week already. So yeah, you know them all, and you've met some of the software liaison as well. Besides one, the software engineering liaison, Alice Bertini is about to retire. So I do not know yet who is going to replace her. And for the Paleoclimate, because Paleoclimate is so diverse right now, there's no strict liaison, but if you go on the Paleoclimate working group, you'll see some names appear there, and you can contact them at any time. And Esther Brady is one of the Paleoclimate working group co-chair that you're going to meet during the Q&A panel this morning. There's a catch though. Whenever you become part of a working group, at least that's how we do it in the land ice, what we're going to ask you is to present your work at one of the CSM workshop, whether it's a winter meeting or the summer meeting. Now, like I said, so we have 2 annual workshops that happens every year in February and June. And it's going to be this way in 2021. The February workshop is more like per working group. So while the summer workshop is the entire CSM community that gather in Boulder, or it used to be in Breckenridge, but lately it's been in Boulder, and it's other working group meetings at once over several days. And it's a great place to make some connections, to get good networking, and to meet your fellow constituents. So I highly encourage you to come and show us what you've been up to. There's a mailing list that you can register to get some news about the CSM community. And you can just register by clicking onto this link. You can post your questions that you have about CSM on this bulletin board, and I'm going to click on it so you can see what it looks like. You have this board here, and people are just posting their questions. And after you post your question, you just tell us which working group it's relevant to, and then one of us will try to get back to you as soon as possible. And if you're looking for allocation on Cheyenne, there's a link here that will tell you all about how to do it. So I want to give many thanks again to all the tutorial organizing committee that made all this week possible, but also Elizabeth Faircloth for the admin support, for Ryan Johnson for the web support, for NSF for funding it, and all the computing folks, the speakers and helpers, and the developers, but also you guys who volunteered and stick throughout the week to make this possible. It was very good to see you so involved, and I hope you guys learned a lot and enjoyed this week. And I hope you will enjoy your last day. So, and hopefully see you at another CSM event. I'll leave it at that. And if you have any questions about what I just spoke about or about today, please go ahead, unmute yourself and ask your question.
Hi, Thank you very much for organizing this, first of all. I just wanted to know when you want the response for the survey, because I may not be able to do it before September. So is there a deadline or?
There's no strict deadline. The sooner the better. But if you can send it to us like within a week or 10 days, or that'd be great.
Okay. Thank you.
And we'll try to send it out to you as soon as possible.
I was gonna say, often we send it by the end of the afternoon practical session. So like if you just, take 10 minutes this afternoon, if possible, that way you can get it done as soon as you're able.
Yeah, it should be fine. Thank you.
In regards to the survey, this is Elizabeth. I'll keep it open for, for about 2 weeks just to make sure in case you happen to miss it.
If you need to fill your coffee mug or tea mug or water, whatever, please go ahead. We're going to start the Q&A panel in about 4 minutes.
Yeah, I don't think we have all the people yet, so
yeah,
we should definitely wait till 9.
I can see Dave and Kate. Good morning, Dave and Kate.
Salut, bon matin.
Bonjour.
Gunter, I had a quick question about continuing to run CSM. So we have a certain number of hours, you're saying, and we can extend that. And then is there, I guess, how do you apply for more funding? I don't know if you could talk about that a little bit.
Yeah, so there are 2 ways to apply for fundings. First of all, if you're funded by an NSF grant, then as a graduate student, without making a big allocation, without having to ask for a big allocation, you can ask, you can email Cism and say, I'm a grad student, I'm funded by an NSF grant, and they would give you a few 100,000 core hours for you to run your experiments. You need to be, so yeah. And then that's something I still need to clarify. Maybe Dave or Alice, you might know this. It was my understanding that if you were at a US institution, or if your university was part of was UCAR affiliated, then as a grad student, you could just ask for core hours without having NSF funding. That's still not 100% clear to me, and I will email Dave Hart about this because the website is not crystal clear.
I can chime in. I am a student and I was able to get a small allocation request basically just by submitting a letter from my faculty advisor and then I think like a brief abstract on what I'm working on. I can put the link here. Oh, I think it's the page that's up right now.
I cut and pasted the link.
Thank you, Dave. Yeah, I was going to say I went to the website here so you can see it, but it just says resources for unsponsored graduate students, postdocs, and new faculty. So if your advisor doesn't have funds, you can still request time. You can request up to 400,000 core hours. So this is like a small allocation request. If you want more than that, you have to do what's called a large allocation request, which is a different type of proposal. But you should, I think that they're pretty open and willing to having unsponsored graduate students and postdocs who want to use the computer and the models for, interesting new science. So.
Great, thank you so much.
Yeah, and that small data request, Alice just about paged down to it there, but there's also just, it's just a data only, like if you want to get access to the large ensemble and things like that, then you can get a data access allocation as well. That's like super easy.
And if anyone is teaching, or if any of you are new faculty, we know some people who request classroom allocations, so that if you're teaching like usually this is like a seminar, a small class, then you can get time so that you can actually use the model for your class as well. Elizabeth, do you know, or Gunter, do you see if everyone's here? I see Betty's here, Dave's here, Kate was there.
I don't see Bill. Is Bill,
There's
are you
Esther. I don't see Bill yet either. Is Bill the last one we're waiting for?
Yes.
Yes, okay.
Bill was taking some PTO this week. I know he said he was going to be here, but I don't know if he was planning on.
Yeah, he said he would be like not 100% on, but.
Okay. He may not want us to wait for him. I don't know.
Okay.
He typically likes doing this.
He likes these things, is that what he said?
Yeah, he likes the tutorial.
Well, I went through, so as I've met, I think I've met about a quarter of you at the Meet a Scientist things now, but I'm Alice. I'm one of the Polar Climate Working Group liaisons. I work a lot with trying to understand the polar climate, mostly the sea ice, but I also think about interactions of the sea ice with the ocean and the atmosphere, how they all talk to each other. So I'm moderating this session today. If you hear weird noises, my dog, again, is whining at me a lot today. I don't know why, but yeah. So the first, I'm going to the poll questions that you guys put in there. The first question, I've just sorted them by what are the top ones. So I wanted to go through these ones first. I think this is pretty similar to what you guys have done in other days. And then if there's a follow-up question, I guess I'd ask you to raise your hand, and maybe Elizabeth or Gunter, if you guys are able to see in the chat, or if there are hands raised, if there needs to be something else addressed, that would be helpful if you can bring it up, because it's not always easy to see. All right, so the first question is a paleo question. So Esther and Betty, this is probably for you, but the question is, what's the current understanding of carbon cycle feedback in paleoclimate? How can we design experiments to quantify its impact on climate using CESM?
Want me to start, or you want to start?
Yeah, Betty, you better take this.
I think there's still quite a bit of uncertainty in this. It is really a coupled process. So you need to know what the land surface is doing, what the ocean is doing. Some earlier, more simplified models suggest that you need to consider not only the physical properties of, for example, the ocean, temperature and salinity, but also the biogeochemistry of the ocean. So if one wanted to design an experiment, I would suggest two things. One, kind of try to simplify it. So don't try to just try to understand why carbon dioxide was lower during the last glacial maximum in a fully coupled system, but think of maybe what is the effect of the actual atmospheric CO2 or the ice sheets, or that. You can actually run the model where you look at the carbon cycle feedbacks without changing the radiative forcing. So for example, the atmospheric CO2. But to do this project well, you'd want to assemble a team, or get set up maybe a Zoom call in this virtual world with not only those in the paleo group, but those in the, for example, the ocean biogeochemistry groups.
Anything else to add, Esther?
No, not really, but I do want to let people know that we currently have some carbon isotopes, isotope tracers simulated in CESM. We have some radiocarbon and carbon-13 in the ocean. It's quite expensive to run, and so we haven't really ourselves had much experience running it with CESM2 in the ocean tracers with the biogeochemistry in the ocean. But we also have an abiotic version of radiocarbon that we have been running in our CMIP6 simulations, our mid-Holocene and our last interglacial. And we also have carbon-13 and radiocarbon in the land model tracers. So, that might be a way to get started looking at the carbon cycle for Paleo, just comparing the model simulation of these tracers to the Paleoclimate proxy data that's out there. Anyway, just wanted to add that in and let people know. I'm not sure if it was covered in the tutorial.
Okay, thank you. And I just wanted to say I'm able to put a little arrow here pointing to which question we're answering. So if you guys go away and then come back and you're wondering, because I'm not able to make them go away on this list. So the next question is a sea ice question. So me or Dave, I'll let Dave start. The question is, if I want to compare the sea ice from the CESM1 large ensemble with the sea ice in the CESM2 large ensemble, are there any major changes in the sea ice model I'd want to account for that might impact the comparison?
I was gonna say Alice should start on this one, but anyway, no, that's fine. I guess short answer, yes. But I will say, so there's new thermodynamics. We've changed the vertical levels in the sea ice and snow. And so the new thermodynamics have a prognostic salinity, which before it was a constant salinity. And so there's a lot of changes just internally in this sea ice itself. And I actually have a manuscript that I'm working on now that hopefully will be out in the next couple of months. But the idea is that I did just a comparison of only the thermodynamics and the changes in the sea ice. However, that said, there's changes in the rest of the system that have really big impacts on the sea ice in terms of comparison. Like the atmosphere is quite different from CSM1 to CSM2. The ocean model is pretty much the same, but generally the changes in the atmosphere are having a really big impact. And I think Alice has done some work to address that aspect. And then also Hansi Singh has a manuscript that is in review now that also compares some of this, but in the Antarctic. So, I don't know if Alice wants to add on to that.
I don't think I have anything else major to say. I mean, I think as Dave brought up, if you were comparing two model versions like this, two large ensembles with different model versions, there's a whole slew of changes between lots of different components. So yes, there are differences in the sea ice component, but there's also major differences in the atmosphere component and stuff too. So you should really treat them as like two entirely separate models. It's not like kind of same versions of the different versions of the same thing. That's not really what they are. So I think that is probably good for that one. In the interest of continuing on, let's see. Stop. I'm trying to be careful about this and then it. Okay, so the next question is a land ice question, and it is, what is the radiative transfer scheme in Cism? How is the albedo of the ice surface calculated if it is not spatially and temporally varying to include various light absorbing impurities and melt ponds? How can we trust the projections of the ablation zone under warmer future conditions? So Bill or Gunter? I don't see Gunter anymore, so. There you go.
He's still.
There you were. You were. I don't know why I couldn't see you for a second. We're good.
Sorry, could you repeat the question, please, Alice?
Yep. So it's the one that has the blue arrow next to it. It's what is the radiative transfer scheme in Cism? how is it's a series of questions.
Right.
How is the albedo of the ice surface calculated? If it is not spatially and temporally varying to include various light absorbing impurities and melt ponds, how can we trust projections of the ablation zone under warmer future conditions?
Okay, I'll take a stab at that. First of all, Cism doesn't have a radiative transfer scheme because the snow and the firn that sits on top of the ice sheet is handled in the land model CLM. And so everything that applies to seasonal snow in CLM also applies to snow on the surface of an ice sheet. It uses the Snicker radiative transfer scheme, which is developed by Mark Flanner, is my understanding. The albedo of the snow is calculated by this radiative transfer scheme, which I'm not too familiar with the details, but it's documented in the CLM documentation. If you melt all the snow and get down to an ice surface, the ice albedo is treated very simply. You just have one albedo value in the near infrared and another in the visible. I think those are, do you remember the values, Gunter?
Sorry, say that again.
Yeah, I was just trying to remember the values we use for the near infrared and visible light.
Not on top of my head.
For ice
no.
sheets, something in the neighborhood of 0.4 to 0.5. So we don't have anything spatially or temporally varying on the ice. But as I say, we do have light absorbing impurities and percolating meltwater in the snow.
Great.
Bill, I can add a little bit more on
Right.
if you would like.
Sure, please go ahead.
So the Snicker scheme is snow and ice radiation, I think it stands for. It's also quite similar to a radiative transfer scheme that we have in the sea ice, which is the Delta Eddington formulation. But the idea is that it receives incoming shortwave across different bands, so visible, near infrared, far infrared, so forth. And it breaks that down, and then it actually computes an albedo in each band, and then figures out the fraction of different surfaces when it's doing it. And then it does an actual multiple scattering within the snow and sea ice to determine the net absorbed shortwave. And then at the end of that iteration, you end up with the resulting albedo and absorbed shortwave. So there's actually an effort to try to unify these radiative transfer schemes between the land and the sea ice. And Charlie Zender's group at UC Irvine has been doing a lot of work on this.
All right. So we'll go on to the next question. Another paleo question. What are the main differences between paleoclimate models and historical/future simulations? For example, some physical processes may be important or critical to paleoclimate models, but they are negligible for historical/future simulations. Esther or Betty?
I can say at NCAR and for CMIP6, the model we use for the paleoclimate simulations and for the historical and future is the same model in terms of its dynamics, its physics, its parameterizations. We do not change anything for CMIP6. That's part of the protocols of CMIP6 because they want to be able to assess their simulations for the future from what we know from the past, where we have data that's much longer, usually more extreme or out of sample than you'd have in the historical. What is different is the forcings and boundary conditions we give the model, and those are critical. The model is only as good as what you give it sometimes. So if you give it the wrong aerosols or what you know about paleogeography, it's going to affect your simulation. In the paleoclimate modeling intercomparison world, we call that the PMIP triangle. You have uncertainties in the models and how they're constructed and what processes they include. You have uncertainties in the data, how it's interpreted, and you have uncertainties in the boundary conditions, you know, how big the ice sheet is, what the paleogeography is, what the vegetation and aerosols are. So for CMIP 6, I can say that's what we do. That's not to say we don't explore, and I think maybe this is the next question, improving the fidelity, explore the parameterizations within our models. So many of you may have met Jean Zhu, who was one of the team working with you this week as you did your tutorial. And he's looking at things, for example, in terms of the parameterizations of clouds and convection, and how when we use them to look at like a past cold climate, some of the challenges in using the model as it's currently been tuned to present day. So that's an example of the second question there.
Anything to add, Esther? I will say we kind of moved to the question below this too, which is how can we improve the fidelity or simulation skills of paleoclimate models? What is NCAR currently working on about it? So
I think Betty talked about what Jean is doing to understand you know, that the effect of cloud processes on climate sensitivity and how the paleoclimate simulations he's done reflect some understanding of that. So I know Jean is currently working on that sort of thing. In general, like going on to the next question about paleoclimate model proxy comparisons, that is something we do. The paper that we're about to submit back our revisions on, which is details the CMIP 6 mid-Holocene and last interglacial simulations that we performed. We do have a pretty large section on how the model compares to the proxy data for the annual mean estimates that are out there, and also the summer signal that's in the proxy data, how the model compares to that. I think, you know, that in that paper, we look at it pretty simply, just a straight comparison. I think Betty can probably talk more about the proxy data uncertainties as compared to the model. But that's generally what we do. So
I can just
Betty wants to add something.
I can just add there, and it's actually both of these questions. The other way we use to improve the fidelity is to work with our university partners. For example, the tidal mixing at the last glacial maximum might be different than it is today. And university graduate students have worked on that, looking at the sensitivity to that process and how it affects the ocean circulation. In terms of the discrepancy, yeah, I think the important thing here is it's a two-way understanding. The models aren't perfect, but neither are the proxies. And so using them together and trying to understand the processes in the model, sometimes with more simplified versions of the model, is really important to do, and try to understand what the proxy is actually telling us about the climate system, because often we assume a proxy is just temperature, but it probably has some biology in it. There's some sedimentation type differences. And an important lesson, which you're all too young to remember, but I do, is tropical, I forget what it's called, the paradox, tropical paradox under warm climates. It was Cretaceous. So very high CO2, very warm climate. And yet the proxies, what's it called?
Cold tropics paradox.
Cold tropics, yeah. The models were saying it should be warmer when you force it with higher CO2s. The proxies were saying the tropics should be cooler. Well, they found out that the proxies had been altered and during their sedimentation with time, and it actually was hotter. So I think it's important to keep an open mind and try to understand why there are differences.
All right. So the next question is sort of spans all of these topics. It's at the top here. Why do we need an isotope model? Without an isotope model, we can still use CESM to simulate temperature, ice volume, ocean heat content, etc. I assume there should be a question there asking, can we still do all those things without the isotope model? So Esther, do you want to head that one up?
Yeah. Well, we currently don't have the isotopes in CESM2, so that's something we would like to continue in implementing. But what the isotope model, well, there's a couple things. For Paleo, having the isotopic tracers in there gives us a better comparison to the actual proxy data measurements. It's more direct. So for example, the delta 018 that's measured in ice cores can be compared more directly to the delta 018 of precipitation over the region where the ice core is collected. In the ocean, instead of going from the delta 018, say in the benthic sediments, to deep ocean temperature or ice volume, we can directly compare the delta 018 simulated in the ocean to the sediment. And so it gives a better comparison to the proxies. And so we sort of alleviate the inference or the interpretation that you have to make going from the proxy to the physical climate systems. Because as Betty just said, the proxy isn't just measuring temperature, it may be measuring something about a change in the hydrologic cycle or in that relationship that is used based on modern climate to go from the proxy to the physical climate state. And so that's what an isotopic implementation gives you in the climate model when comparing to proxy data. However, like in the atmosphere, Jesse Nussbaum has shown that the isotopic tracers in the atmospheric model can really tell you about some of the processes and how well we're simulating some of the processes, for example, stratospheric, tropospheric exchange of moisture, and you can directly compare the simulated isotopes in CAM to some of the modern data collected by satellites and airplanes. So it helps in understanding the processes, and it helps in comparing to the paleoclimate record. And does anyone else want to add to that? Betty or anyone?
Maybe Bill or on the ice sheet model, or Gunter? No.
I don't think there's anything to add for us.
The only thing I would say is that the isotopes provide another tracer in the system, which is a really nice thing. You can trace water from its origin through the land, through the sea ice, and it's a really nice way to track motion through the system in sort of a Lagrangian sense.
Right, and it has been used to look at moisture sources. For example, how they may have changed the sources of moisture to the monsoon regions in the past, and can be used to track. Yeah.
I'll just add one thing. Something we'd like to do in a future version of CESM is have isotopes passed from the land model to the ice sheet model, so that we could, whatever is in the snow then works its way into the ice. And then once we have the isotope content in the ice sheet model could affect isotopes downstream, and then you could potentially compare to ice core records. But we don't yet have the capability to pass isotopes to the ice sheet model.
Right, yeah.
Maybe I'll add one more thing, because I think it was part of this question. Isotopes is an option, but if it's something you don't want to look at, you don't have to run CESM with isotopes. So it's a option that you can use or not, depending on your application.
All right, thanks for that thorough answer from the different groups here. The next question is sea ice. What are the limitations of IOPs, meaning ice optical properties? Are there any plans to move towards more physically based representations of sea ice optical properties? So I'll start, and then Dave can weigh in. I was going to say that Dave mentioned earlier, we're working on more of a unification of the different radiation schemes, the snow radiation schemes and the sea ice compared to land and stuff like that. And so I would say that that's one movement. There are also projects right now that with people we are collaborating with, getting observations. So like the Mosaic cruise that's going on right now in the Arctic. There are collaborators up there taking albedo measurements and snow property measurements and stuff like that. And so the plan is that that data will be used to try to develop more physically based representations of what's going on in terms of the snow melting and its temperature and all of that on top of sea ice in terms of affecting the albedo. Dave, do you have anything else you want to add there?
Sure. Yeah. I'm happy to take this discussion offline too with the person who asked this, but I would argue that what we have is very physically based already. It was done based on the Sheba observations. And so similar to what Alice is saying with Mosaic, they took ice, snow, melt pond, optical properties, and they designed a scheme, and you can read the Brigleb and Light technical note from 2007. It's very detailed into how they derived all the optical properties and everything. I would say the only limitation, and that's why they're doing it on Mosaic, is that this was all done based on Sheba, on one site and one set of measurements done during that Sheba campaign. And so it's not as applicable even around the Arctic maybe, or definitely not for the Antarctic. And so I would say that's the main limitation. And so the only way we can really improve this is by adding more observational information into this.
Great. Did you have something to say, Bill? I see you unmuted yourself.
I'm waiting for the next question.
Okay. He's anticipating. All right, so we'll go on to the next question, which is there already coupling between the ocean model and the ice sheet model? Bill.
Yes, there is partial coupling. And the partial coupling that we have now is that when the ice sheet model is being run interactively with the rest of the climate model, and you have calving from the ice sheet model, that calving flux, the solid ice flux, is sent to the ocean, and the ocean then has to use heat to supply heat to melt the ice, and the ocean freshens accordingly. So that's what we have in released versions of CESM. We also have a branch, a developmental version of the model, where we're starting to do the coupling in the other direction from the ocean model to the ice sheet. The problem we have with coupling the POP model to ice sheets is that POP doesn't circulate in ice shelf cavities. It doesn't circulate beneath floating ice. But what we can do is we can take a temperature salinity profile at the edge of the ice sheet, where you have basically a vertical wall at the at the calving front, we can take that temperature salinity profile at a certain number of ocean levels that we decide are important, and we can pass that temperature salinity to the ice sheet model. And then the ice sheet has a couple of parameterizations it can use to convert that temperature and salinity into a melt rate, which it can then use to melt ice at the base of an ice shelf. And then the coupling that we'd like to have in the long run would be where you have an ocean which actually changes its shape, its geometry, as its boundary with ice sheets changes. The POP model doesn't have that capability, but MOM6, which is going to be the next ocean model in CESM, is able to do that. And in idealized settings, we've done some experiments where you have a floating ice shelf up against the ocean, and the ocean and ice shelf exchange heat, and the ocean and the shape of the ocean the ice shelf cavity changes. And what we'd like to do eventually for CESM3 is make that a capability in the global climate system.
Great, thank you. All right, so the next question is a paleo question. Where does external forcing, for example, greenhouse gases and LULC, which I don't know what that is off the top of my head, come from for the paleoclimate models? How to quantify the bias or uncertainty caused by imperfect forcing data? Esther.
You want to start that one, Esther?
Me. Yeah, so usually the data that we use comes from, for example, in CMIP, data sets were prepared for use in the simulations for greenhouse gases and land use, land cover. And then someone in-house has to take the data and put it into the format that is needed for input into the model. And if you would like to use a different data, you would have to seek out your own data source or estimate for greenhouse gases. But there are a number of data sets that can be used that exist online through different projects and collaborations. Eddie, you want to handle the quantify the bias or uncertainty, since you talked a little bit about that earlier?
Yeah, the way we have done it in the past is where we are considering that there may be imperfect forcing data. For example, in the last millennium, there's quite a bit of uncertainty in the volcanic forcing because it requires using ice cores in Antarctica and Greenland and deposition in those ice cores to try to determine if a volcano went off at high latitudes or low latitudes, when it went off. And so we can do sensitivity experiments in terms of the amount of the emissions, but also considering, since we don't know exactly where it went off, we can vary the latitude and longitude of where it went off, and even the month, because often in more ancient volcanoes, we don't really know, we just know about the year it went off. So it's doing a number of sensitivity experiments, and you could do the same with greenhouse gases, especially you go deeper in time, there's quite a bit of uncertainty in the greenhouse gases. So looking at different levels of atmospheric CO2 or methane.
Okay. There's another paleo question here. I'm just trying to see how many other things there are. How do you take into account a younger sun and slightly different chemical states of the Earth's ocean and atmosphere when simulating many millions of years in the past? What are the major changes compared to today's Earth that need to be considered? And I think we can answer this one. And then I noticed that below there is a question, how can I change the topography? For example, close the Bering Strait. So I think that could be answered in the same one. Like, how do you decide what to do when you're simulating an experiment millions of years in the past?
Yeah, and I think the one right below this is also very similar.
Yes, the Earth had a different rotation So are you guys okay answering all three of those kind of in the same discussion?
Yeah. So I can start with the first two. I'll let Esther do the topography one maybe. So right now we will work with geologists who tell us the sun is getting brighter. We specify that, and we use the data that they have that tells us, how less bright it was 100 million years ago or 300 million years ago. So that's how we account for that. The same thing with the chemical states. We either can specify it because we know, for example, that the ocean was more saline last glacial maximum because sea level was about 120 meters lower, and that water was now in ice sheets in the Earth's ocean. We also sometimes will use other models like the Megan model to simulate how the chemical state of the atmosphere may have changed under different climates. So we use a bunch of, I would say, data or offline tools to be able to do make these changes. In terms of the rotation rate and the axial tilt, you can change the axial tilt, you can change kind of the time of perihelion, but changing the rotation rate is more difficult. But there are efforts to do this, in particular, Dan Marsh, who's a senior scientist in several groups across NCAR, is looking at early Earth and extrasolar planets. And so he wants to alter some of these aspects of the either our early Earth or other planets. But and he's working at trying to simplify the way to do that. So I would say, in terms of that, stay tuned or contact Dan. And Esther, you want to comment?
Yeah, I'll try and handle that changing topography question quickly. So it's probably one of the more difficult changes that we have to do to in paleoclimate. For example, the Eocene and the Cretaceous all have different continental configurations, and depending on the layout of the continents, it might require changes to the ocean grid. Right now we have a displaced pole grid where the pole is placed in Greenland. And if the continents are changed really radically away from that, you would have to place your pole elsewhere in another continent. And we do have software to do this. It's kind of tricky to use. It's on our, it can be found through our Paleo resources link on our webpage. It goes to a GitHub repository where there's a number of different steps you can follow to create a new land ocean mask and grids that go along with that. And then all the mapping, all the domain files and all the mapping files that you need to run CESM. And there are recipes for that that can be found on the GitHub. But it's definitely quite an involved process. And it's not super easy to do. But the recipes do exist on our GitHub. And I think you can probably just head there. And I think Christine used to show this as part of the tutorial, maybe in years past. Or Matt Rothstein might have given a lecture during a past tutorial. So there may be information in past tutorials also to do this. So you can look through what's available in past tutorials.
I wanted to point out that I'm guessing Gunter has brought this up, but we have the CESM discussion forums as well, where questions like this have already been asked and you can see what the responses are. And I would say not infrequently, there are questions that come up like, I set this up and something didn't happen. And it turns out like, oh, you changed the land boundary. And so you don't have sea ice initial conditions in the right spot or something.
Right. Yeah, like it changes everything.
Yeah.
You really have to go through the whole step you know, to prepare all of the input data sets that you need to run the model, domain files and initial conditions, pretty much everything. So yeah, I'll point you there for more information.
And I'll just add there, and I see there's a similar question. When Esther points you there, be sure to read it carefully, because how you might do something for more recent past climate like the Quaternary, where the continental boundaries haven't changed, but you just want to lower a mountain range or that, are different than if you want to start with a much different paleogeography and move things around. So be sure to read from the top to the bottom to make sure the steps you're doing are appropriate for your problem.
Yep. So that was the answer to that question. I just put a little arrow by.
Mm-hmm.
All right. So the next question at the top is, how exactly can different geologic processes be accounted for? That is transfer between mantle and crust and surface, or output from volcanoes. So we have in the atmosphere volcanic forcing files in the historical, and there are also like background, you know, average volcanoes and stuff like that in the pre-industrial. Tell me if I'm wrong, but my understanding is we don't do anything geologic. We don't have any energy transfer between the mantle and the crust and the surface. I think at this, you know, in the bottom of the ocean, there may be a very small heat flux, but I'm not actually even sure that's included here. So someone else might be more wise about that.
No, you're correct. I mean, eventually one would want to include not so much this transfer, but solid earth processes, and that as ice sheets change and that. So there is isostasy under the Greenland ice sheet, but in general, we don't do any of the geologic processes.
It already costs a lot of computer time to run as it is, guys. All right. Based on the presentation, going to extremes in the new Arctic, have you analyzed the processes leading to these extreme changes in sea ice, surface temperature, and rain versus snow? And I believe that this is a presentation recorded by Laura Landrum, who's not on this call. So Dave and I will handle this. But I would say that in general with the sea ice model, yes, we are investigating all these processes, all of them by looking at energy budgets and mass budgets, and, you know, designing other experiments where we change, you know, something small. So I would say yes. Do you have anything else you want to say about that, Dave?
No, I don't really have much more. There's a paper led by Marika Holland and others. It's probably 2010 now, I think. Anyway, it was several years ago, but they looked at these abrupt drops in sea ice, or what Dave Lawrence has referred to as RILES, or rapid ice loss events. In terms of the rain and snow, there's been some work on potential changes in the hydrological cycle at high latitudes. But I think I will add that this talk that Laura was giving is based on sort of a cross-cutting theme that we have in CGD, which is on high latitude extremes. And I think the idea is that they want, you know, input and collaboration into this sort of cross-cutting working group to try to advance the state of knowledge in this area.
All right. So the next one is an ice sheet model question. What kind of data is used to calibrate Cism at the Antarctic interior? I
guess I'm wondering what interior properties we're talking about. The ice sheet has the interior obviously has a temperature profile all the way down to the bed, which is something that's very hard to measure because you have to drill, and you can only do that in a few places. Also at the bed, you have a certain slipperiness, and how slippery the bed at the surface, whether there's water at the bed, for example, is again something that's hard to measure directly, but it can be inferred from the surface velocity. So generally, I'd say that we use surface velocity and the measured thickness of the ice sheet to determine either whether our spin up has whether we've accurately captured the temperature or the basal friction. Alternatively, since we know so little about the basal friction on a continent-wide scale, we can use the thickness and measured velocity of the ice sheet to invert for or to nudge the basal friction parameters in the model. So for example, if we're wanting to spin up Antarctica for say 10 or 20,000 years, and we don't know what the basal friction is, we have a technique where we start off with a uniform basal friction field everywhere, and then we increase or decrease the friction as needed to get the ice sheet to be the observed thickness. So for example, if the ice sheet is in our spin up is getting to be too thick in some region, we can decrease the friction, and then the ice in that region will slide more quickly, and then the ice sheet surface will fall and more in agreement with observations. When we're spinning up, we often do invert for the basal friction. We generally don't invert for the temperature. We just let the temperature evolve, given what we know about the geothermal flux at the bed from geothermal models and the surface temperature. Is there anything you would add to that, Gunther?
Nope, you covered it all.
All right. So the next one is another land ice question. The presentation about land ice showed a spin up of 50,000 years for the Greenland ice sheet. Given the presence of floating ice shelves in Antarctica, is the spin up time for the Antarctic different?
No, not significantly. The spin up time is determined by the part of the ice sheet that takes the longest to turn over between when snow falls to the surface and when ice flows out to sea or melts at the surface some thousands of years later. In the case of Greenland, it's a little arbitrary how long you say the spin up takes, because things change slowly for a very long time. But after about 15 or 20,000 years, the further changes are very small and don't affect the sensitivity of the ice sheet to climate change very much. And it's similar in Antarctica. After about 20,000 years, the temperature profile is just about equilibrated and not much changes after that. The ice shelves themselves, since they flow pretty quickly, up to several kilometers a year, the ice in an ice shelf will have a relatively short turnover time compared to the rest of the ice sheet. But the total spin up time is determined by the slower flowing land-based ice, which has the longest residence or turnover time.
Great. And then a similar vein, what is the spin up time for sea ice? Dave, do you want to?
Yeah, I'll tackle this one because it looks like the next three are for you. So, so the quick answer is that about 10 years is enough to sort of equilibrate the sea ice seasonal cycle. There are sometimes coupled interactions with the ocean where we can see oscillations in the sea ice at like 100 years and that sort of thing. But generally, to get a sort of reasonable seasonal cycle, that's what we look for. That just takes about 10 years. So.
All right. So the reason I stopped sharing was that the next ones all ask about the sea ice specific slide numbers. So I don't know the slide numbers off the top of my head, which is why I'm looking around right now. We are almost done, so I'm not sure if this is one that would be best. Whoever asked these questions, we could ask it offline because I know that the schedule is relatively tight. Were there any questions that came up in the chat or anything, Ryan, in I'm totally blanking on the name right now. Slack. That's the word. No.
Let's see. One for the land exercise C, and if you want me to share my screen real quick, I can.
Is it for this afternoon's exercises?
I think so. It says land exercise C.
Okay, I think that's probably for this afternoon. So let's hold off on that. We'll just try to answer, I guess, these last few questions here. So the question was slide 16, how is the ocean ice stress obtained? Here, what do CU, CW, and theta represent? So that's in this equation that I'm showing you right here. You guys are seeing my screen. Basically, I'm going to be a little fuzzy on this because I haven't spun up because you guys watched the video instead. But these are the heat capacities here, I believe. And this is like a velocity difference that you're seeing in the ocean ice stress. So, so this is the heat capacity of water. Where's CU? Oh, CU is up here. I'm totally blanking on what CU is.
That's the drag coefficient.
Thank you.
Yeah.
Yeah, and this one is the drag coefficient of water. Thanks.
Yeah.
And then sea ice modeling slides 28 to 30. Let's see. 28 to 30. So can we explain in more detail the ice thickness distribution, evolution equation, and how to interpret a PDF of ice thickness? So basically, the way I think about this, and Dave, you can say if you explain different, is when you're looking at this PDF in green, you're seeing the probability that you have ice in these different, the X scale here is different thickness categories. And so if you have a spike here near 0, that means you have like a high probability of having ice that's basically very thin or open water. And then you have very little in this 0 to 1 meter range. And then you have another peak here, what we're seeing here in this approximately 1 meter size, and then a smaller probability of having very thick ice. And then that drops off dramatically as you get to very, very thick ice. You don't usually have like 10-meter ice floating around. Dave, is there a different way that you think about this?
No. But I think the important thing to emphasize here is that we can't represent this as a continuum. So we represent this discretely in the model. And so we pick in advance how many subgrid scale categories we can use to represent this continuum. So what we do is in our standard model configuration, we have 5 subgrid scale categories. And what we do is we say, well, this is the fraction amount of ice that's in that subgrid scale category. And that's sort of analogous to these peaks of what Alice is talking about. So we would have the fraction of very thin ice, the fraction of slightly thicker ice, and then finally the largest category 5 is for the fraction of the thickest ice available. And that's all within a single grid cell. And so we carry that information around within each grid cell. And then the way that that is moved around, and Bill might even want to chime in here, is that there's an advection scheme that takes that PDF or discrete PDF of ice information and moves it around and then interacts with grid cells around it and so forth. And so it's that's basically all I would add. And then I would go back to the stress stuff to talk about just a little more general about this. So this is sort of like a standard quadratic drag law that's typically used. And so the idea was, this was back from the Hibbler 79 paper, and I encourage you to read it if you're having trouble sleeping at night. But basically what it is that you have a little boundary layer over the ice, and it's sort of a little Ekman layer, and there's the geostrophic winds above the ice, and then there's this representation of how the winds sort of turn within that Ekman layer. And then that's what that cos and sine terms are representing, is that sort of turning in the boundary layer. And below the ice too, in the ice and ocean, there's a similar Ekman layer underneath. So that's sort of a more sort of general view of how these terms are derived. And they're very similar to any sort of stress interactions over the ocean or even over land or whatever. And then I think they also asked about the sea surface tilt term.
Yep.
And that's just basically representing if you have waves or something, or some sort of pressure gradients where the sea surface height is different spatially, then the ice is going to tend to slip down those slopes just due to a gravity sort of argument. And so that's...
I now visualize this part as, I don't know if any of you guys have children, and if you haven't, you might still have seen Frozen 2, but there's a part where Elsa creates this like ice thing in this really stormy water, and then you can see like the ice is moving around. That's a nice way to think about it to some degree. So, okay. All right, well, that was all of the questions. We're past our time by about 5 minutes, so sorry, Gunter, if we're messing up the scheduling here, but I think that's it. Thank you for getting through. That was your last Q&A, and I wanted to say thank you to all of the experts. You guys are talking to the co-chairs and the liaisons here who know the model inside and out. So thank you so much for spending time to come answer questions. We really appreciate it.
Yeah, thank you so much, Alice, for moderating this last session. Thank you to all the panelists. And so I know it's almost 10 and some of you will meet with scientists, but as I announced this morning, it would be great to have a Zoom picture from everybody. So it's optional, like I said. If you could turn on your camera right now, and Ryan would take a picture of all of us. Good to see you, everybody.
We aren't talking to empty screens. That's good.
Okay, so I'll wait for everybody's camera to load in. And so there's 2 pages, so I'm gonna have to do 2 screenshots. So Gunter, you are right about that. Let's see. Okay, so everybody's in. Everybody's loaded. All right, so is everybody ready? Everybody got their camera on that wants to be in the picture? It's like we got a good bit of them. Okay, so on the count of 3, I'm gonna take a couple of them. So just keep smiling, hold your hand up, or do whatever, okay? All right, 1, 2, 3, cheese.
Homage.
All right, next page, 1, 2, 3. All right, I think I got everybody. One more for good luck. All right, that's a wrap. Thank y'all.
Thank you so much. So if you want a quick 2-minute break before you meet with your scientist, please go ahead. It's 9:58. Elizabeth will assign you to your breakout rooms. Okay. And I hope you have a nice session then, and I will see you back for the office hours.
Sounds good.
We don't have all the scientists yet for office hours.
Yeah, Precious is here, Bill is here. So we're missing Laura and Jesse. Is that right?
Yes, exactly. That's why I was double checking.
Yeah, we still have a couple of minutes.
Yeah.
So Elizabeth, we're staying on this call for the next hour? Okay.
Yes.
Yeah, we'll stay on this. We'll give it a few minutes, and then I'll go ahead and open the rooms. So you'll get that invite, and that will send you and your participants off to your breakout room. And within that, it functions just like a regular Zoom meeting. You can share screens, ask them to turn on their cameras. They can turn on and off their microphones. And yeah, we've gotten good feedback on the sessions so far this week. Lots of good conversation. You're really engaged. And so you kind of have the benefit of having them on the last day. They're really comfortable with each other and have a lot of experience now under their belts.
Could you remind me, Elizabeth, after they go to breakout, will they be coming back at the end to the main session again, or do we just adjourn from the breakout?
They can come back to the main room. You know, we've left that open as their networking opportunity, and I haven't yet seen any topics for discussion suggested yet. So maybe they're getting tired, or maybe we'll get some more topics. I did put that. You know,
Everybody's working on
out there.
all the practicals for this afternoon, so.
Yeah. Yeah.
Hi, Jesse. Hi, Laura.
Hi.
Hi, Gunter.
So one question. So are they meeting different scientists every day, or a different group meets scientists a day a week?
No, everybody can meet different scientists every day.
All right.
And it's not set. They sent us some preferences on whom they wanted to meet with.
All right, right.
It was up to them to meet with as many scientists as they wanted.
Oh, sounds good.
I'm just double checking.
All right, whenever you're ready, Elizabeth, send everybody to their room.
Okay, sounds good. I just
to your room.
I lost Mary Beth. Where did she go?
She's here.
Yeah, in my.
Yeah, I'm here.
Okay, good. Yeah, no, I was just assigning you to the room with Precious. So, well, I'm going to go ahead and open up the rooms. If for some reason you didn't bounce to your room and you're supposed to, just send me a chat really quick, and I will fix it for you. And again, if anyone in the breakout rooms has any questions, you can go ahead and call for help, and I'll bounce into your room. Okay, have fun. Everyone should now have an invite. Oh, I found Mary Beth. She got sent to Laura instead of Precious, so I just moved her.
Okay.
Hey, Gunter, so we're using the Slido link for later today?
So I will take a look at what's there, and then it sounded like people thought it would be a little bit easier.
Zoom?
Yeah, to just use the Zoom chat.
Okay, yeah, there was 2 this morning and then 2 from last night.
Just a second. I think Chloe needs to go with Bill. At least she signed up to go with Bill.
Mm-hmm.
Yeah, thank you.
Yeah, okay. I knew that I was double checking, so no worries. I just bounced you there.
Thanks.
Yeah, and Giovanni asked to go to the session with Precious, and he had a spot open, so that's okay, right?
That's fine.
I don't know that Giovanni went to